Hello everybody, let us talk about the lens. Lens, it is also the transparent medium. Okay, we already talked about the refraction of light. So the light can refract through the lens also. And there are basically two types of lens. One is like this. Thick in the middle, like this, thick in the middle right here. It is thick in the middle, and this lens we call convex lens. Convex lens. And there is another lens thin in the middle. This is thin right here, thin in the middle, and you can draw like this. Something like this. So this is your concave lens. So we have normally two types of lens. Convex lens, thick in the middle, thin in the middle. This is concave lens, this is convex lens. Both are transparent, you know that. Okay. So these, sometimes you can draw like this. It is easy to draw the ray diagram. Okay. So this is a concave lens. This is also called as the diverging lens. Diverging lens. And this is called as the converging lens. Converging lens. Okay. Like we talk about the spherical mirror. There are two types of spherical mirror. One is concave mirror. Concave mirror. Concave mirror is something like this. Concave mirror, and concave mirror is converging mirror. The concave mirror we are called converging mirror. Converging mirror. Okay. Another one is we have a convex mirror. Convex mirror is like this. This is your convex mirror. Convex mirror, and this is called as the diverging mirror. Diverging mirror. Okay. So here convex lens is converging, convex mirror is diverging, don't confuse. Okay. Concave mirror is converging, but this concave lens is diverging. Okay, so please don't confuse. Okay, so two types of lens, concave lens and convex lens. And let me talk about the convex lens. So this is one surface of the lens and another surface you combine like this. Okay, so you have a one curved surface, another curved surface, you combine like this, then look thick in the middle, that makes a convex lens. Okay, and there is the center of the lens, you can call optical center or pole of the lens, and if you draw the line passing through this point and perpendicular here and perpendicular there, if you draw the line like this line, it is perpendicular here, perpendicular there, you have to draw the tangent there. Okay, so this line is called as the principal axis. This is your principal axis. Okay, then axis of the lens, if I draw the ray like this ray is parallel to the principal axis, another ray is also parallel to the principal axis, and these rays, they are coming from the distant object. What does that mean? Object is really very far. Okay, these rays, they are parallel, this ray and this ray, they are parallel to the principal axis, and these rays are coming from the distant object, very far distant object. Object at infinity, you can call that. Now, these two rays pass through the convex lens. What happens is, this ray it goes like this, and this ray also passes through the same point here. Both rays, after refraction through the lens, they converge right here, and this point you can represent by F, and this point is called as the focal point. Okay, so the parallel rays, the parallel to the principal axis, after refraction through the convex lens, they focus at the focal point, or they converge at the focal point. That is why this lens is called as the converging lens. If you draw another ray parallel to the principal axis like this, all rays, they pass through the focal point like this. All rays, they pass through they converge right here. Therefore, this lens is called as the converging lens. So, if you take the ray from this side like this, then you have another focal point here. So, on either side of the lens, you have a focal point. And as you know that, if you measure the length from here to there, this length is called as the focal length of the lens. The length from the center of the lens to the focal point, we call that focal length. And the reciprocal of focal length, like 1 divided by focal length, 1 divided by focal length of the lens, this gives you the power of lens. Power of lens is 1 divided by focal length. So simply you can write down 1 divided by F. So this is the power of the lens, and the unit of power of the lens is 1/meter, and that is called diopters. Diopters is the unit of power of lens. For example, if you wear the glass, okay, this is the lens. It depends on your eye, like your defect, what types of defect you have. Accordingly, the optometrist, he or she gives you the eyeglass, convex lens or concave lens. If you are wearing the concave lens glass, the power of the lens is negative. If you are wearing the glass having convex lens, the power of the glass is positive. Anyway, the power is 1 divided by focal length, and the unit of power is diopters. And here I am drawing the convex lens, and the convex lens is called as the converging lens also. So here, where is the image? Object is really very far. We call the distant object. So where is the image? Image is right here at the focal point. And in this case, if your object is really very far, then in that case your image is very small, almost like a point size. And simply the image formed by convex lens is real image. The image formed by the convex lens is real image. Does it mean the convex lens always makes the real image? Not necessary. Look at this. Let us suppose this is the convex lens, and this is the principal axis, and there is a one focal point here and another focal point there. Okay, from here to there, this is the focal length, or from here to there, this is also the focal length, and they are equal if it is biconvex lens. If it is biconvex lens, This length is equal to this length. If you keep the object right here, this is your object O prime, this is object. Can you complete the ray diagram? How do you draw the ray diagram then? Okay, one ray you can draw parallel to the principal axis. This ray I take from here and it is parallel to the principal axis. If the ray is parallel to the principal axis, after refraction, that means passing through the lens, it passes through the focal point like this. Another ray, if you take from this point, center of the lens, it passes without any deviation, no deflection. It simply passes in a straight line like this. One second. It passes something like this. Then what happens? This ray, this is a refracted ray, this is also we can call refracted ray, but they diverge. My diagram is not quite good, but they are not parallel here, okay? I have to use a ruler, okay? So they diverge. Then what happens in this case is if you extend this line and extend this line like this, these are the dashed line and the image formed here. This is the image I prime, but this image is the virtual image. This image is the virtual image. So if you keep the object inside the focal point, right here, not here, right there, inside, then in that case the convex lens can make the virtual image also. But in most cases, the convex lens, it makes the real image. What is real image? The image that can be obtained on the screen. Like if you keep the a negative there, film there, you can obtain the image there. You can obtain on the screen. That is called as the real image, and the virtual image cannot obtain on the screen. So the convex lens, it is the converging lens. It makes the real image. And the real image is normally upside down, inverted. For example, let me draw one more. Like, let us suppose this is my convex lens. This is my convex lens, and you draw the principal axis. There is a focal point here, and there is a focal point there. And if you keep the object right here, little bit behind the focal point, then in this case, one ray you can draw like this, parallel to the principal axis, and it passes through the focal point. Okay. Another ray, if you take from the, let's say from here, from the focal point like this, you pass it from here, from the focal point on the same side. So the ray parallel to the principal axis, after refraction, it passes through the focal point. Now another ray, it passes through the focal point on the same side of the object. Then after refraction, what happens is it becomes parallel to the principal axis like this. So this ray, it is parallel to the principal axis, and your image is right here. This is your image I prime. This is your object O prime. And it is again better to use the ruler, okay? So here I just use my hand so I don't get exact size of an image. So you can see that this image is upside down. This image is real. So the convex lens, it produces the real image. And normally the real image is upside down, or we call that inverted. And if you keep the object at different position here, the size of the image is different. So we can define the magnification. This is, you can write down M. This is size of an image divided by size of an object. Size of an image divided by size of an object. So it is simply, people they can also write down like I divided by O also, size of the image divided by size of the object. So if the magnification is 1, for example, if you get magnification m equal to 1, what does this mean? This means size of the image and size of the object, they are equal. If you get magnification 1, that means the object size and image size, they are equal. But if you get m equal to 2, what does this mean? This means the size of an image is 2 times bigger than size of the object. So the magnification is size of an image divided by size of an object. So this is the definition. Or the magnification you can also write down like this. Magnification is negative this of I, this is image distance. What is image distance? The distance of an image from the optical, from these points, from the center of the lens. Image distance divided by this of O. This is the object distance. This of I is the image distance. You measure the like this. This is your image distance. From center of the lens to the image, this is called as image distance, this of I. And from center of the lens to the object, this is called as the object distance. So the magnification is negative of this of I divided by this of O. This is also the magnification formula. Or simply you can write down size of an object and size of divided by size of an size of an image divided by size of an object. That is the magnification. So if magnification is 3, that means the image is 3 times bigger than the object. And if the lens has the focal length f, f is the focal length of the lens, this of O is the object distance, this of I is the image distance. So there is a relationship. The relationship is 1 divided by f, 1 over focal length, this is equal to 1 over this of O, object distance, plus 1 over this of I, this is your image distance. We call this formula, this is a formula to calculate the focal length, to calculate the object distance, to calculate the image distance. This is also called as the thin lens formula. So you can use this formula if you have to calculate the object distance, image distance, and focal length. And please note, the focal length of the convex lens is taken as positive. The focal length of the convex lens is taken as positive. It is the sign convention. The focal length of the concave lens, that is diverging lens, is taken as negative. Again, the focal length of the convex lens is positive. Focal length of the concave lens is negative. Okay, so to solve the problem, we have to apply the sign convention also, but this is the formula, thin lens formula. This formula is good for both lens, concave lens and convex lens, but of course we have to apply the sign convention because the focal length of the concave lens is taken as negative. And if the image is virtual image, in that case the image distance is also negative. But if the image is real image, then the image distance is positive. Okay, so anyway, please note down this formula, thin lens formula. This is helpful. Okay, so what I was talking about is, if you keep the object at different position here, the size of the image is different. The location, where do you see the image, that is also different. Like if you keep the object here, image from there. If you keep the object, for example, right here, maybe your image is at infinity, really very far. Okay, so this is about the convex lens. The formula is same for the concave lens, but of course you have to think about the sign convention there. Now the concave lens, which is thin in the middle, and that is also called as the diverging lens. Let me draw one ray diagram. Okay, this is a concave lens, and you can draw the principal axis. So this is principal axis, here is the focal point, there is another focal point like this. Then what happens is, if you have a concave lens and the rays of light after passing through the concave lens like this, look here. So let us suppose this is the ray coming from the object at infinity, distant object, very far. And this is another ray. Look, these two rays, they are parallel to the principal axis. What happened is, they refract fast because this is a transparent medium. So what happens? It goes like this and this goes like this. But these refracted rays, this ray and this ray, they appear to diverge from here, from focal point. Appear to diverge from focal point like this. Look, they appear to diverge from this point. This point is the focal point, of course. The refracted rays, they appear to diverge from this point. That is why this lens is called as the diverging lens. And the image formed by concave lens is virtual image. Okay, that's it. So this is about the concave lens. So you don't need more than this about the lens. So we talk about the spherical mirror, we talk about the lens, we talk about the critical angle, total internal reflection, refraction of light, Snell's law. Now I want to talk a little bit about the interference of light. Interference of light. You know, the light is the electromagnetic wave. The wave always, like a sound wave, okay, like a light wave, they show the property, interference, diffraction, like reflection, refraction, polarization also. But please note, sound wave never polarize. Sound wave never polarize, but of course light wave, light waves polarize. Okay, but here I want to talk one property, interference of light. We already talk about the reflection and refraction things. Okay, so what is interference of light? So if one wave is coming from this way and another wave is coming from, they mix up, they interfere. That is what we call the interference. Okay, now let us suppose the light wave, one wave, first let us do like this. This is the wave, this is the wave, and this wave has amplitude, let's say A here, and moving in this direction. This is the amplitude, and let us suppose another ray B, amplitude is B, and moving in this direction. They meet somewhere here. Then what happened right here is the amplitude A and B, they added up like this. You get a really big. So this amplitude, this is A plus B. So they mix up here, and the amplitude A and this amplitude B, they added. If this is 2 centimeter and this is 2 centimeter, then this becomes 4 centimeter. It's big amplitude then. So what happens if the wave interfere like this, like a light wave coming from here, light wave coming from there, and they interfere like this? In this case, you see a really very bright spot there. We see really very bright there. And after interference, what happened then? So this is your now B, this is your A. No change, nothing, exactly the same. This length and this length is same. Okay, this length and this length is same. But right here they added, and the amplitude becomes B. And right here, if it is a light wave, you see a really very bright spot there. We call bright band, or you can say bright fringe also. If it is a sound wave, one sound wave coming from here, another sound wave coming from there, then if they interfere like this, you hear really loud sound. And these types of interference is called as the constructive interference. Constructive interference. Okay, the same phenomenon, constructive interference, if you want to use different way, different ray diagram, I mean wave diagram like this, you can do this. This is one wave, and another wave, let us suppose, is also similar. if they mix up, like this is a crest and this is a crest, the crest fall on the crest fall on the crest, and this is trough fall on the trough, this is trough and this is trough, crest. So the crest and crest, like you can think about like a ripple, one ripple like coming from this side and another ripple they coming from this side. So if the crest of the first ripple fall on the crest of the second ripple, you see really big one. That is a constructive. So same as this, the crest fall on the crest. So if you want to figure out the resultant here, the resultant is, let me erase this. So if you want to figure out what is the resultant, this is one wave, another wave, they mix up, but crest fall on the crest, trough fall on the trough, and your result is, actually let me write down this direction. So the result is really big. This, you get really big wave. This is the constructive interference. This is constructive interference. Okay. And another one is destructive interference. What happened? Let us see. Destructive interference. So there are two types, constructive and destructive. So let me use this. Let us suppose this is wave A. Moving in this direction, this is wave A. And you have another one. This is B. They mix up somewhere here. Look, it is up and this is down. If they mix up here, what happens? This is a crest, this is like a trough. They cancel out. So if they mix up right there, so you get just like a dot. Nothing. And after interference, what happens? This is your A. This is A and this is B. But here they cancel out. So if it is a light wave, if this is a light wave and this is the light wave and they interfere here, you don't see anything. That is like a dark spot there. And this is called as the destructive interference. If you want to draw the different diagram like this, like this. Now look at this. This is a crest. Crest fall on the, this is trough. Crest fall on the trough. And here this is a trough. This trough fall on the crest. So this trough fall on the crest. And here this is a crest fall on the trough. So this crest cancel the trough. This trough cancel the crest. This crest cancel the trough. So what is your result then? Your result is simply nothing, like this. So this is also the destructive interference. Same thing, this diagram and this diagram. That's the different way of drawing only. So destructive interference, they cancel out. Okay. And the interference of light, there is one experiment we call the Young's double slit experiment. Okay, so that is like, let us suppose this is double slit. So you have to make one slit. This is a slit, okay, like a slit opening, like you can say like this is like a plate, and so this is like an opening. We call the slit. But there are two slit. One is, let me call this is S1 and this is S2. Two slits. So this is double slit then. That is why we say Young's double slit experiment. Young's double slits experiment. So this is a double slit. You have two openings, okay, and somewhere there you have a screen, and the distance between the this is the center of the screen. This point is the center of the screen. Okay, let us suppose the distance between the slits and the screen is L, and to observe the interference pattern, there is some condition. All light you cannot observe the interference pattern. You need the coherent source, like a laser light. You need coherent source of light. What does this mean? You have the same wavelength, same frequency. So like a laser light, you can use a laser light. Okay, so the laser light is coming from here like this. We cannot use the visible light because visible light has a 7 colors, different colors, 7 colors. If you have a different color, you have a different wavelength. You cannot observe the interference pattern there. So we need the single wavelength light, that is a laser light. Okay, so now what happens is, the ray, one ray, if you take from here, from this slit, and another ray from this slit, you take here, from the opening S1, and another ray from there. So two rays, they mix up here at this point P. Okay, and let us suppose the distance between the slit, this distance we call slit separation. If this distance is D, this is a slits, the distance between the slits, you can say slit separation. Okay, and this ray coming from opening S1, slit S1, and another slit S2, they mix up here. Then what types of, we call fringe, what types of spot you observe here then? If they interfere like this, so if they interfere, crest fall on the crest, trough fall on the trough. Look, crest fall on the crest, trough fall on the trough, crest fall on the crest, trough fall on the trough, crest fall on the crest, trough fall on the trough, so crest fall on the crest. So in this case, you observe right here, this is bright fringe, or you can say bright band also. Okay, here now if you another band you can observe that, but that only you alternately you observe bright and dark fringe. So if the wave interfere, if the light interfere constructively, at that point you observe the bright band, bright fringe. And condition to observe the bright band is d sine theta, this is equal to m lambda. This is a condition to observe the bright band, d sine theta equal to m lambda. What is d? This slit separation. Where is theta then? Theta is, you can draw from here to there, you can draw the line. One second, you can draw the line. This angle is theta. Okay, this angle is theta. And what is m? We call the order of interference pattern. So with this band, if this is a second band, third band, fourth band, whatever, if this is a fifth fringe or fifth band, then m equal to 5. We call the order of m. This is order of interference pattern. Okay, theta you can see here. D is the slit separation. What is lambda then? Lambda is the wavelength of light used. Lambda is the wavelength of light you have used there. Wavelength. So this is for the constructive interference. Constructive interference. And for the destructive interference, destructive you can write down d sine theta. This is equal to m plus half lambda. This is for the destructive interference. Okay, so please note, if the two wave they interfere constructively, if it is a light wave, then you can see a really bright band there, and if two light wave interfere destructively, you see the dark spot there. Okay, so this is the condition. You don't have to focus too much this formula, just I am writing here. So this is the very brief discussion about the interference. Similarly, the light wave, they can show the property of diffraction. Like, what is diffraction? Diffraction is something like the bending of light around the corner of an, you can say, aperture, like this. Like if you have some kind of like a blade like this is like a blade here, and if the light is coming this way, and if you have a screen here, light is supposed to go like this, but right here light bends little bit like this. The bending of light around the corner of an aperture, this is the aperture, like a very sharp edge, the light bend a little bit there, that is called as the diffraction. And light also polarized, but mainly with the like a reflection, a refraction, interference. I think that's good for you. Okay, I think that's all about the interference. Okay, then I'll bring another video. Thank you.